then another one, right? How about now? Can you find the word happy in this paragraph, which is much more longer than the one just now? Oh, not very difficult, but I will take longer time than before, right? Because it's longer, right? How about now? If you need to find the word happy in these two paragraphs, okay, it will be more difficult compared to the first two, right? Okay, so you can see, and let's say now I want you to find the word happy or a certain word in, let's say, a text, okay, that contain, let's say, 10 pages, 20 pages, 30 pages. So you will take some time, right? It doesn't mean that we cannot find, but just that it will be much more, it's a tedious task, right? You need to spend more time to look at it, right? If your data or your text, you have more and more text, right? Okay, or even you have to find it in this whole book, right? You can imagine how long it takes you, okay, to find all this, right? But what if, okay, can you find the word happy in this list of words? Oh, very easy, right? If I can put all the text just now in this form, then to find happy is very easy. Okay, I will just go to the word that start with H, and I will just look inside this list only. The list, the word in this list here. Do they have a happy? Yes. Yeah, so there's a happy here. If it's not here, you cannot find the word happy in this list here, then it means happy doesn't exist, right? You don't have all these other word lists to find, because H, if your word start with H, it will only be here, right? You just go to this, it's like this column only to look for it, or this row only to look for it, right? Okay, so now you can see that, why we want to impose structure on data. So that after you impose, right, when you want to perform certain algorithm or certain task to this data, it will be easier for you, okay, compared to if you just use the raw information only, okay. So this is data structures, right? How about the algorithms? Algorithms is actually a finite sequence or the step-by-step of a well-defined instruction. Typically, we use it to solve a class of specific problem or to perform a computation, okay? And here, for this, for this whole workshop, we will look at algorithms that is related especially to sorting and searching, okay? So as I'm just overview, this is what, these are the topics that we are going to have. Advanced workshop, we have, let's say, 4 workshop, right? So we will cover data structures and also algorithms. For data structures, there will be 2 workshops. Okay, so today we are going to look at this workshop 1 that we will cover on linear data structures. Okay, like list, stack, and queue. And then the second workshop, we will cover non-linear data structures, like trees and graphs. And then for the algorithms part, for workshop 3 and 4, we will cover 2 different algorithms, okay, searching and sorting. Okay, for searching, we will look at linear search, binary search, and hash table. And these are the sorting methods that we are going to look at in general. Okay, so now, okay, let's go to what is a linear data structure, right? So linear data structures, like I think in the first few slides, I have told you that it's linear because one data can only connect to one data here. When you impose the structure, okay, like you can see here, the diagram at the top here, data are linked from data 1 to data 2, data 2 to data 3, and then 3 to 4 until, let's say, n, okay, to data n. But it's only 1 to 1, okay? Then we call this as the linear data structures. For non-linear data structures, okay, you can see here, tree will be an example of a non-linear data structures. Why this is non-linear? Because one data here can be connected to more than one. For a tree, and this is a binary tree. So one data here can be connected to 2, okay, or at most 2. Okay, like this one is connected to 1 only, or some is not connected to anything. It's okay, but the maximum is 2 for a binary tree. Okay, But in general, non-linear data structures mean one data can be connected to more than one. Okay. And today we are just going to look at non-linear data structures. Okay. So first we look at what is a list. So if you look at this diagram here, this is the most simplified list representation. Okay, like you can see here, A1 connect to A2 and so on until AN, right? So a list is a linear sequence, right? As you can see here, 1 to 1. And how do you represent it? If you want to write it formally, this is how we write it. L equals to A1, A2 until AN, where N is the size of your list or how many data you have in your list, right? And this N value must be more than or equals to 0, which means that you can have a 0. 0 means the list is empty. Okay. Then you can have a one data, 2 data, 3 data, and so on. Okay. And all these data that you store in each of these, like A1, A2, will be the same data. Okay. And each element here, like the rectangle here, usually we call it as the element or node. Okay. It will be number. Okay, like this is node 1, node 2, node 3, and until node n. And then the connection from, it will be, you can go from element I to I plus 1, like element 1 to 2, element 2 to 3. And at most go from element I to element I minus 1. Means besides going from left to right, forward, like 1 to 2, 2 to 3, you can also go backward, like 3 to 2, 2 to 1. Okay. And then we have empty list when your n is 0, which means you don't have any node yet added into your list. Okay. Now let's look at two types of different list concept here. Okay, so over here. Okay, so for example of this, let's look at these two lists of antique Chinese coin. Let's say we tie it up together using string. Okay. We look at the one on the left first. Okay, the one on the left, it will use only one string to actually tie up all the coins together, right? And you cannot cut the string in the middle. If you want to take the coin out or you want to insert a new coin in the middle, you cannot do that for the one on the left-hand side here. Okay, if you want to take out a coin or you want to insert a coin, it can only be done at the beginning or the end. Okay, you cannot do it in the middle. So this type of list, okay, is what we call as a specialized list or like stack and queue. Okay, it's the model for the data structure of stack and queue, where the insertion and deletion of the items or the coins like in this case here, it can only be done at the beginning or the end. Okay, but the one on the right hand side here, this list here, right? Okay, you use many string to type. So you can always insert and also remove the coin from in this list here. It can be middle, it can also be the beginning or the end or somewhere in the middle. Also, you can perform your insertion and deletion. And this is what we call as a general list. Okay, so in summary, you can have two types of, you can say, lists. A special list, we call it as a stack and queue, okay, where the insertion and the deletion of the data can only be done at the beginning or the end. And then the general list, you can insert and remove anywhere in the list, beginning, end, and also in the middle. Okay, so usually for list, right, some of the basic operations that you can perform on a list after you build the list, right, then you want to perform some operation to it, right? You can of course first you must be able to create the list. Okay, then you can initialize your list, okay, or you check whether your list is empty, search, of course, insert and delete, the most basic operation, right? Or sort, and then traverse means how do you go to every node, visit every node in the list, because a lot of operation you need to know how to traverse the list as well, right? Okay, so what can I do with list? after I build the list, right, why I need this list? I'm talking about the list here will be general list. Okay. You can, of course, use it to simulate any real list of items. For example, you want to store, let's say, a student information. Like in your class, right, there are 20, 30 students. So if I want to store all the information of the student, I can put all of you in a list where every node represents one student. Like every node, I will store your name, maybe you have student ID, right? Your address, your age, and so on, right? Or the price list, purchasing price list, okay, subject list, okay, and so on, so on, so on, right? Or book list, okay. You can also use it to simulate abstract list in computer operating system, like the job queue, print queues, okay, or implement integers of unlimited size or polynomial representation. For example, long integer, you can see if you need to deal with your programmer, you need to deal with this kind of long integer, where if you just use the normal data type, it's not enough for you to store because of the size, right? Okay, then what can you do? You can just represent this integer using a list where every node represents one digit. Okay, then you can use it to perform arithmetic operation between the integer, okay, where one list you add with one list. One list represent one integer. Okay, so you have two lists, each represent one integer and one integer. Then you can write program to perform arithmetic operation to it. Or you can use it to represent polynomial expression. Okay, so at the end, one of the example for linked list, we are going to see how to use linked list to represent polynomial expression. Okay, like here, how do I represent? You can set the AI, which is the coefficient, to be the I digit or the I component of the polynomial. Like each node will represent one of this expression here in this polynomial expression. Okay, we will look in more detail later at the end. Okay, for our special kind of list, we now remember what is special kind of list. Okay, this list, you can only perform insertion and deletion at the beginning or the end, cannot be in the middle, right? So we have two types, right? Queue and stack. So for queue, it has the property called first in, first out, or FIFO. Okay, why? Because for queue, let's say, for example, queue, like the real queue, right? A queue of customer or people will queue. When you queue, for example, the first person that arrive will be, and then whoever join later, you have to join at the back, right? You can go to the beginning and then you join that, right? So you have to go to the, will be the first one that will be served first, right? That's why first in, first out. Okay, it has this property. And then for stack, it has the property called last in, first out. Okay, so this last in, first out, right? You can see like a stack of chair. Why it has last in, first out property? Like the stack of chair. Okay, when you have this stack of chair, now if you want to put a new chair to this stack of chair, where do you put? On top, right? You just put on top. Okay, and then now if you want to remove a stack of chair from this stack of chair, you will take out the first one, right, which is the last one that you just put in. So that's why it's called last in, first out. Okay, we will look at queue and stack later after we look at the general list. Okay, then let's see. Okay, what types of linked lists or general lists that I can actually create? Okay, the most simple one is a simply linked list. So a simply linked list, like you can see here, this diagram here, tell you how a simply linked list looks like. One node here, this rectangle here represent one node where you store one data. And why this is called simply linked list? Because the connection is from left to right only. Okay, it's 1 to 2, 2 to 3, 3 to 4. You cannot go back. Okay, so this is simply linked list. Then beside this, you can also create a doubly linked list, like this diagram here at the bottom. Okay, how is it different compared to the simply linked list? You can see here for this doubly linked list, you will have the connection from right to left as well. This one is only left to right. This doubly linked list, you see, I can go from 1 to 2, 2 to 3, 3 to 4, right? Let's say from 4 now, I can go back to 3 because I have this connection that allowed me to go back. Okay, that's why we call this as a doubly linked list. So it's designed to provide access to the next node as well as the previous node, right? This is only next node. Okay. To implement this, you need 2 pointers. Means you need to have later you will see what is pointers. A pointer that store the address of the next node and also the previous node. In syncly linked list, you only need a pointer that store address of the next node, right? Okay. Then another type of linked list that we can create is called a circular linked list. Okay, why this is called circular? You see, how is it different compared to our syncly linked list just now? Okay, our syncly linked list just now is 1 to 1, 1 to 2, 2 to 3, and so on, right? But this one is called circular because when you go until the end, right, this last node, usually the connection here, we set it to now, so that to indicate that, oh, this is the last node. You cannot go, there's no next node anymore. So this next node here in the last node, you set it back to point to the first node. So it's like when you go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, from 5, you can go back to 1 again. It's like a circle. You see, that's why it's called circular linked list. Okay, and the most complicated linked list that you can create is what if this list here is a doubly linked list, like the previous one. Okay, so you can go from 1 to 2, 2 to 3, right? And then you can go backward, right? So if you want to make this doubly linked list to be circular, you just set this pointer in the last node next, point to first one, and the previous pointer in the first one, you point to the last one. Okay, you can also do that for a doubly linked list to make it circular. Okay, so these are some of the types of linked lists that you can create. But when you have a circular linked list, you need to be careful because when you perform operation to it, you can go into infinite loop, because the thing is, when you process each node one by one, right? So when you go to the last, you process until the last one, it leads you back to the first one. So if you're not careful, you go back to the first one and then go to 2, 3, 4, 5 again, then 5 go to 1 again. It's like a loop, like your infinite loop. Okay. So this one you need to take note. Okay, so when you look at the linked list, you find that it's very similar to array, right? You know array, right? Okay, then how is it different than array? Why don't I just use array? Why do I have to use linked list, right? Okay, so this table here show you some of the differences between linked list and array. So for example, linked list supports sequential access. Okay, so it will be slower when you access item. What is sequential access? Means you have to go from one data can, first data can only go to second data. Second data can only go to third data, one by one in order. Okay, so that's why if you want to access the last item in your linked list, how do you do that? You have to start from the first item, go to second item, third item, until the last item. So you can imagine how long it takes. It depends on how many items you have in your list, right? But for array, it has random access. So when you want to access any element, it will be very fast. You will use the same time to access any element. Okay, random access here means, let's say your array have 100 elements. You want to access the first item, the time it takes is the same as when you want to access the last element, right? Why array can do this? Because array are stored contiguously in memory next to each other, so that whenever you want any element, you can calculate the address and then just go to it and access. But linked list cannot. Okay, later you will see each of these item here, right, or the node, we call it as a node, okay, will be stored differently in memory. So that's why you use this what we call as the next, which is a pointer to store the address of the next node. So that's why when you are in first node, you only know where is the second node. You don't know where is the third, fourth, and fifth. You can't know that. So that's why you must use sequential. From 1, you can only go to 2, 2 only go to 3, and so on. Okay, so that's why it will be slow. Then linked list is unlimited size, because every node we use dynamic memory. So as long as you still have memory, you can always increase a node or add a node to your linked list. But array is limited. Usually when you declare array, you have to specify the size, right? Okay, so that's why if you specify your array to be size 10, then you can store up to 10 elements. You cannot like, I want to add or I want to delete. You can't do that. Okay. And just now, as I mentioned, every node in linked list will be stored randomly in memory because we use dynamic memory to create every node. But every element in your array will be stored in contiguous memory. Okay. But linked list, one of the advantages is, if let's say when you store this list and you always need to insert and delete items in the middle of the list, then linked list will be a better choice because it will be easier to insert and delete items. Okay, but array, insertion and deletion of your element in the middle or basically anywhere is much more difficult. Because if you want to do this to array, you have to original array, you copy to a new array, then of course you insert whatever data you want in any position that you want. I mean, a lot of copying that you need to do if you do insertion and deletion of element in array. Okay, so the choice is yours, which one you need to use. Okay, you have to consider all these things, okay, for linked list and array. Then you make your decision whether you want to use linked list to implement or you want to use array to implement it. Okay. Okay, so before I go to our first linked list, right? Okay, we will look at the implementation. First, we look at what is a pointer. Okay, what is a pointer? So pointer here is similar to the wheel of fortune. You know, wheel of fortune is something like this. You just okay, push this thing and then it will stop, and then depends on this pointer is when it stops, it points to which one, right? So here, this pointer here can only point to one. So the pointer that we learn is this pointer. We say we use a pointer to point to a variables, but and this pointer we can always change it to point to a different variable, but it can only point to one variable at a time. Okay, so let's see what is pointer. So pointer, it is also a variable. When you say I declare a pointer in my program, you are actually also declare a variable. But how is it different compared to the conventional variable that you declare? Okay, the conventional variable you declare, you use it to store data, right? Like you declare integer int a, so this a can only store integer data. You declare a float b, so this b only can store float, right? But pointer, what is stored inside? Address of another variable. It is not used to store like integer data, float data, character data. It is used to store address of another variable. Okay, and how do I declare this pointer so that I know, oh, this is actually a pointer? When you declare a pointer, you just have to put the name of pointer, of course, like here we call it as PTR, and then also the type, and you have to put this asterisk here, so that you know that whenever you declare a variable, if there is not those conventional declare. Okay, like here I declare double asterisk PTR. Why do I need this type here? Because I'm not going to use the pointer to store data, right? I'm going to store the memory address. So the type here is to indicate this PTR can store what variable memory address. So if I put double, it means PTR can only store address of a double variable. For example, here, let's say I have a variable D1, which I declared earlier, like float D1, and then I assign value 1.53 inside. So if I want this PTR to point to this variable, how I do it? This is the assignment statement. PTR equals to not D1, ampersand D1. Because the ampersand is used to indicate address of a variable. So, and because our PTR is a pointer and is supposed to store address, right, of a variable. So here, when you do the assignment, you want PTR to point to D1, you have to put ampersand D1, not D1. If you put D1, what do you assign to PTR? 1.53. D1 will be the value of the variable, right? But if you put an ampersand next to it, it means the address of this variable. Then this is the correct assignment. This is how you should do it. Okay. Then here, this PTR can only store address of a double variable. Like if let's say you have another variable INTA, can you make PTR equals to $A? No. Okay, you will get error if you do this because the type doesn't match. Here we say that PTR can only store double variable address. Okay. Okay, so and usually how we draw the we say that PTR is pointing to D1, right? In diagram, this is how we draw. But actually, what is the meaning when we say PTR is pointing to D1? Actually, what I store in D1 is the address of the variable D1. Okay, let's look in more detail. Okay, for example, let's look at another example. Let's say I declare another pointer PTR1 type integer, and I declare a variable A equals to 3. And then I declare another pointer PTR2, which can store address of a variable person. This person is a struct person that we declare outside, right? And then I declare a person P. So then these two statements, I make PTR1 points to A, and then I make PTR2 points to P. Okay, I put it in a diagram to show you after these two statements, right? This PTR1, right, is pointing to this variable A. Assuming that, let's say, our variable A, the address is 7890. So what I actually store in PTR1 is the address of A inside. But conceptually, when we draw the arrow pointing to A, right? And then the value inside A is 3, right? Because here I initialize it to 3. And for my this PTR2 is points to a variable of type person. So let's say my type person in this struct person, I only have 3 members, name, phone, and money. And this is the value that I assign to P. Like name is called Alice, phone is 12345, and money is 300. So when I make this assignment P2 equals to ampersand P, so I'm storing address of P, assuming the address of P is 6732 inside this PTR2, right? So after these two statements, this is what we have, okay? Now, when I try to see out, let's say I have PTR1 points to A, PTR2 points to P. So if I see out ampersand A, address of A, right, I will get 7890. If I see out PTR1, you will see that it will also have the same value as this ampersand A because it stores the address. This is, you can try this just to verify that PTR1 is pointing to A because it stores address of A inside. Same also for this PTR2. Here, sorry, there's a typing mistake that this one should be ampersand P, not Alice, ampersand P. And then see out PTR2. These two should have the same value when you see out ampersand P and when you see out PTR2. Okay? And now, how about, let's say, if I see out A, okay, and I see out asterisk PTR1, what do I have? Okay, if I see out A, of course, I will get 3, right? Just now you see, inside A is 3. If I see out asterisk PTR1, if I put an asterisk next to the pointer when I use it, not when declare, that is different. So when I use it, if I put an asterisk here, means I dereference the pointer. Okay, this is the term that we use, we dereference the pointer. So why we want to do this dereferencing? You dereference the pointer because to assess the value in the variable that is pointing. For example, PTR1 pointing to A, right? Inside A, I have value 3. If I want to see out 3, there are 2 ways. One is I see out A, like this. Another way is I can use this pointer to access 3 as well. How? Put an asterisk next to it, dereferencing. So this one also will see out 3, okay? For the second one, also the same. If, let's say, I want to see out name in this variable P. How can I do it? Structure, right? So you put P dot name, right? Access the member variable. Use the dot. Okay. Can I use this PTR2 to access this name Alice? Yes, you can also. You dereference PTR2, but because PTR2 is pointing to a structure type, a user-defined type, not a primitive type like A, because user-defined type inside, you can have many things, right? So you cannot just see out asterisk PTR2. If you just put asterisk PTR2, it means everything inside P. name, phone, and money, and you try to see out, you get error. So you need to be specific. You want to access which one? Okay, I want to access name, right? So you have to put asterisk ptr2.name, or you can simplify it to this statement, ptr2 arrow name. So next time when you see arrow, you know that you are trying to use the pointer to access the name, not the name, the member inside the structure that is pointing. So this one will print Alice. This one will print Alice. This one also will print Alice for you. Okay. So let's look at in more detail. If I try to see out the following expression based on these two assignment of the pointer. For the first one, PTR1 is pointing to a primitive type like A. If I see out ampersand A and PTR1, you will get the address of 7890, the same. If I see out A and asterisk PTR1, you get the value inside it. This one will dereference the pointer. Okay, if your pointer is pointing to a user-defined data type, where inside this variable P, you contain many different things, right? Okay, so if I see out ampersand P, you get the address of P, right? If you see out PTR2, also you will get this address of P, because this is what is stored inside PTR2. If you see out P.name, you will see out Alice, right? If you see out, you put in this statement, bracket asterisk PTR2.name, you access which one, you will also see out Alice. Or in a simplified statement, you can just use an arrow, PTR2 arrow name. It will also see out Alice. This is how we dereference the pointer that is pointing to a user-defined data type. Okay? Can you see out PTR2.name? You can't. If you do this, it means because when you use dot, what you put here should be the structure variable name, like P. But PTR2 is not a structure variable, it's a pointer that point to a structure. So this will cause you error. Okay. So basically, just remember, if you have a pointer pointing to a variable, what is inside the pointer is the address of the variable, and you can also use this pointer to access the value in the variable that is pointed by dereferencing it. Okay, depends on if it's a primitive type, a symbol type like integer or float or character, you just put an asterisk. But if your pointer is pointing to a structure, you can just use this arrow, PTR2 arrow name, to access. Okay, if you want to access the phone, then PTR2 arrow phone. Okay, and so on. Look what is pointer, right? And how do we use it to point to a variable? Then when are we going to use pointer? Okay, here there are 4 ways that you can use a pointer. One is you can use it to store address of the dynamic memory, or you use it to pass the variable to the function, where we call it as pass by address. Or you can use it in later when we use a data structure, right? We use pointer to link items together. Like just now I show you the link list, you see every node you have item and next, right? The next is the pointer that we use to store the address of the next node. Okay, or you use as iterator to traverse the data structures. Okay, let's look at each one. To store address of dynamic memory, this is what I mean. Okay, if let's say here I have an integer A, right? This A is created using static memory. As long as you are not using the new keyword to declare the variable, it is a static memory. So in static memory variable, you have type, name, memory, and address, right? Like the type for A is integer, the name is called A. Memory is the memory that you use to store the variable. Okay, like memory, you need 4 bytes, like usually integer. Address will be the address where this A is, like which chunk of memory is allocated to you in this address, 3276. That's it. So when I want to refer to this memory here, I use the name, right? Like I want to increase this one to 4. Then I just use the name, or A equals to A plus 1, right? I use name of the variable. But for dynamic memory, okay, this is how you declare dynamic memory. New int. It's like you ask the compiler, allocate to me a memory to store this integer variable. So it allocate to you. Then this memory or this integer that is allocated to you, okay, it only have type, memory, and address without name. How do I refer to it? Like I want to assign values to it. How do I do that? You can't, right? Like A, I can use the name A or A equal to 6, but this one no name. How do I refer to it? So in that case, right, that's why whenever you declare a dynamic memory variable, you need a pointer here to store the address that is returned back. So remember just now the referencing, because if you have a pointer pointing to this memory, you can use the pointer to access the value inside here, right? Dereference it. This is how we do it. If you want to assign value 6 to here, you put asterisk PTR equal to 6. Okay. So right. Then the second one is we can use pointer to pass by address to function. Like here, we can test. Let's say I have this function, I pass 3 parameters, pass by value, pass by reference, and pass by address. Okay. How do I pass? Like these 3 parameters x, y, and z. X is passed by value because I only send the value inside to the function. Y is passed by reference, and then Z, this set, is passed by address. So passed by address here means when you call the function the time, you see the third one, you pass the address of the variable C inside this function. So that's why this variable Z inside this test function now, when you come to here, this Z is actually a pointer that is pointing to this C now. Because when you call, you pass in the address of C. So when you dereference this pointer means that you are accessing the value in C. So whatever you change to this asterisk Z, you are changing C in the main head. This is how we can use pointer to pass by address. Okay. Then the third one is how to use it in data structure to link items together, right? Like just now I show you for link list. For every node, right, we have item and next. This next is actually a pointer, okay, that store the address of the next one, okay, and this is how we link up all the nodes together in linked list, okay. Like for non-linear, like binary tree, every node, right, you have 2 pointers, left and right, because you can have it can be connected to 2 data at most. So this left and right pointer, they point to the left child and the right child, okay. Then the last one is used as iterator to traverse the data structures. Like I have the cur here. This cur is a pointer. For example, okay, traverse data structure here means, let's say a very simple task that I want to do to my linked list is I want to print out the content of every node, right? How do I do that? Then I must start printing from the first node, right? What is the value here? Then print the second node, the third node, and so on. And this means I have to go to every node starting from the first one until the last one, right? So then means I need to traverse the linked list, traversing, okay, which means you need to go to visit every node here. So how do I do that? I can create a pointer. Let's say I call it as cur, and I make this pointer point to the first one. And then when it's pointing to the first one, take out the item value, print out. Then move the cur pointer to the next one, take out the value and print out. And I will do the same thing to each node until when it points to the last node. After I print the last node, then finish. You can also do the same thing for this tree here. You can create a curve, point to the root, and then you can move the curve to each node, move it down, okay, when you want to traverse this tree as well. Okay, that's why we say that it is used as an iterator. Okay, here. Okay, so after we look at link pointer, right, I hope at least you have some idea what is a pointer, because when we implement our data structure, we actually need to use a lot of pointer. Okay, now let's look at how do we implement a linked list first. Okay, there are 2 ways that you can do this actually. You can do it from scratch, which means you write everything, you create everything yourself. Okay, if I want to build this kind of linked list, I need 2 structures. One is to represent the node, like one of this node here, and one is to represent the whole list. So to represent the node, I will create a structure called node, and inside I have item and next. You can see an item, let's say, is 8, and then the next is a pointer that store address of the next node. And for the list itself, okay, to represent the whole list, a head pointer which will point to the first node, right? And then I can have the count to tell me how many nodes I have. And here inside, I can implement some function where this function is used to perform certain operation to my linked list. Like I can insert, I have an insert function, remove, size to check how many items I have, empty to check if my list is empty, and other function that you think is necessary. Okay, so if I build from scratch, this is how you should do it, right? And you have to implement every function yourself, and it's not easy, right? Okay, so because of this, right, instead of implementing everything from scratch, in C++, right, they have a library called STL, Standard Template Library. And this STL is like solution to manage collection of data. And also it has algorithm as well. Okay, so instead of building everything from scratch, because I think for now you can try to just use this STL so that your development will be fast. Okay, so in programmer's point of view, this STL is just a bunch of collection class. Okay, and inside let's say you want to create a linked list, they have a library that allow you to create a linked list, and they also provide all those functions like to allow you to insert, to remove items from your linked list, or even to sort and so on. Okay, so let's look at in this STL, right? They have containers. Containers will be the library that define the container to store and manage your data. Okay, so the template for this library, or what containers you can create. You can have array, vector, you can have stack, queue, okay, tag, list, forward list, and all these like map and order map and so on. Okay, so for us here, we are going to look at the stack, queue, and list. Forward list is the singly linked list, and list is actually a doubly linked list. Okay, and provide you with iterators. Remember iterators just now? We use it to traverse the data structures, right? So it also have iterators library that allow you provide you with an object that is like a pointers, where you can use it to traverse the data structures. Okay, and it also provides a set of algorithms, okay, that you can use like for sorting, searching, okay, and I mean a lot of algorithms that you can use here. Okay, now here, because for this first workshop we are going to look at linear data structures, right? So we will look at the sequence container, which means linear in the standard template library. The first three are actually for array one. Okay, you can have array, vector, and tag. You can see the difference. Vector here, the size is not fixed, because usually for normal array, the size is fixed, right? Vector is an array where the size is not fixed, and tag is also not fixed. Okay, but you can add item beginning and end. But what we are going to look at is linked list. So linked list, there are two types. It provides you with list and forward list. Forward list is just a singly linked list. If you declare a list, it's a doubly linked list. Okay, we are going to use this one, the list. Okay, so if you want to know what is inside the STL list, what are the member functions or the functions that you can actually use when you declare a list, you can go to this website. It provides you the list here, including what iterators that you can use. Okay, we will look at some basic operation. Okay, how to use the STL to declare a list, and then how do we add items inside, how do we delete items inside. Just some basic operations only. Okay, so let's look at first, let's look at how do we include this list inside our program. Okay, you can just at the top here include list. Okay, then okay, if I want to create a linked list, how do I do that? Using this STL list. Okay, let's say first you need to decide, okay, your list, right? What data type you want to store in your linked list. Let's say my linked list, every item I want to store one integer only. So how do you declare this list? You put list, then this bracket inside, you specify the data type you want to store inside your linked list. And then this is the name of your linked list. Like here, I declare two linked lists of type integer. So here I put list int list 1, list int list 2. If you want to declare list, let's say to store a person structure type like just now, you can just put list bracket person. Okay, then this one, or you can declare list bracket, let's say a float, if you want every item to store a float. Okay, so it depends. Okay, so this is how we declare a list. And okay, now I also need to use iterators, right? So that I can use it to traverse my list, means to visit every node in my list. For example, if I want to print my list, then I need to have iterator that go from the first node, then the second node until the last node one by one, so that I can print the value in every node one by one, right? So I need iterator. So I will create two. How do you create iterator? You list int, this will match with the list. You want to use this iterator on list one, right? So here must also be int, must be the same type. And then here you put colon iterator, so that you know this it1 is an iterator. Okay, so I already declare to one it1, I use it to iterate my or traverse my list one, and then it2 I use it to traverse my list two, right? Okay, now after I declare my list, my iterator, okay, now I try to add some or insert some value to my list one and list two. Okay, for my list one, here the first for loop, you can see, to insert, you have the function called push back or push front. Okay, here you can see what is the difference. Let's say for list one, I use the function push back. I use a for loop. I want to insert value 1 to 5, 1, 2, 3, 4, 5 to list one and list two. But list one, I use push back, and then I put I. So this is how the value are going. I mean, how we add or insert the nodes to list one. So after I equals to 1, the I here is the for loop I. Okay, the first node I insert will be 1. Then when my I equals to inside, right, and these two will be at the back, means after this one. When you use pushback, right, means every new node that you insert to the list, it will be inserted as the last node to the back. That's why it's called pushback. Okay, so when I insert I equals to 3, this third node will be at the back, then the fourth node and the fifth node. So this is your list one. After the for loop, this is how your list one looks like. First node is 1, then 2, 3, 4, and 5. If I use push front, my list two, I use this function push front to insert the node, right? So after I equals to 1, okay, I have one node only. Then when I equals 2, I will insert value 2 to this list 2, right? And this 2 will be inserted before 1. You can see here, right? Means when you use push front, every new node that you insert to the list will be inserted as the first node, right? So when my I equals 3, you can see this third one will be at the front. When my I equals 4, you can see this 4 also at the front, and so on. So this is my list 2 after I've inserted 1 to 5. You can see that the first node is 5, then 4, 3, 2, and 1. So it depends how you want to arrange your data in your linked list, whether you can use push back or push front. Okay, when you want to add items to your list. Okay, now let's look at we also now I have insert items to my list 1 and list 2, right? Now I want to print the content in my list 1 and list 2 so that I can see what is in the first node, the second node, the third node, and so on. So how can I do that? Okay, I can use the iterator that I declared just now, right? IT1 and IT2. So IT1, I use it to traverse this list 1 and IT2 for list 2. So how do I say that IT1 to traverse the linked list, I must always start from the first node, right? Okay. So here, that's why in the for loop, I can use a for loop to do this. So in the for loop IT1, I will make it to list 1 dot begin. This function begin, when you call it, right? Okay, return you, you can say the address of the first node in your list 1. So that's why after this statement, your IT1 is like will point to the first node in list 1. We do the same for list 2. We make IT2 equals to list 2 dot begin. So both also will point to the first node when we just start. And then what is our condition? Our condition is, okay, how do I know that I have reached the end of the list? Okay, here we use n, list1.n and list2.n. When you put list1.n, it means have you reached the end of the list one or not? So it's like it returned to you the end of the list one. Okay, this one will return to you the end of list two. Okay, and then you need to increase your IT1. Okay, so how do I see out the value? You cannot just see out IT1 because this IT1 is something like a pointer. So it's like you have a pointer pointing to a structure, right? Okay, of this node. So in order to access the value using this pointer, we have to dereference it. So that's why here you have to put an asterisk, IT1. Same also for IT2. Okay, when you want to see out the value 1, 2, 3, 4, 5. Okay, so let's see how this iterator, this IT1 move when you, the first for loop and also for the second for loop, I will show it in parallel. So initially it points to the first one, then when the second time we loop IT1 plus plus and IT2 plus plus, then it will point to the second one, then you plus plus again, it point to the third one, and then fourth one, and then finally the last one, and then it will stop. Okay, because you reach the end already. Okay, and what will be printed out? You will get 1, 2, 3, 4, 5 printed out for list one. For list two, you will get 5, 4, 3, 2, 1 printed out. Okay, right. Okay, beside just now, remember I told you if you want to insert a push back or you can use push front, right? Either you insert it as the last node or the first node. Okay, what if I want to insert in the middle? Because this is a general list, right? I can insert anywhere. Okay, to insert in the middle, okay, how do we do it? There is a function called insert also. This insert, you can use it to insert in any position in the list. Okay, but you need to do something first. For example, now this is my list. My list one, it has value 1, 2, 3, 4, 5, right? And I want to insert this value 16 in the third position. Means after I insert, 16 will be 1, 2, then 16, 3, 4, 5. Okay, how do I insert this 16 in the third position? First, you must use this function called advance. We are going to use the iterator as well, this IT1. So initially, I will make this IT1 equals to list1.begin. So it will point to the first node. Then I use this function advance, okay, which is part of the function member in your list class. So advance, I put IT1 bracket 2, means advance this IT1 2 position from where it is pointing now, because it's pointing to 1, right? So 2 position from here, 1, 2. So after the advance, this iterator will point to here, and then you call insert IT1 16. Okay, so when you call insert, this iterator is like to tell the insert, okay, insert this 16 to the position that IT1 is pointing now. So after this, now this is this one, after the insert. And when we try to print out, okay, after the insert, so I have 1, 2, 16 now in the third position, right? 5. And I try to print out list one so that I can check, right? So this is what I get, 1, 2, 16, 3, 4, 5. Okay, print out, where 16 is inserted in the third position in our list one. Okay. Okay, so what else I can do? Okay, for example, we can insert, of course, we can also remove, right? It cannot be, I can only insert but cannot remove. So to remove value for, let's say I want to remove, there are 2 ways that you can remove an item in the list. One is you can remove based on items value, okay? Items value means, let's say here my list one, I have value 4, right? So if I want the, I want to say, I want to remove this node that has value 4 inside. So how do we do it? You just call this function called remove. List1.remove, you pass in the value of the node that you want to remove. So if you call list1.remove 4, so after that you see, because here in this part of the program, I try to print out list one before I remove. This is what I have, right? 1, 2, 16, 3, 4, 5. Then I call remove 4, then I print list one again. So after that, you see, when I print this one again, the 4 disappears, it's not there anymore because it's already removed. Okay. Or if you don't want to remove according to the item's value, you can also to the item's position. For example, let's say I print out my list one, and this is what I have, 1, 2, 16, 3, 5. And now I want to remove node in position 3. Position 3 will be this 16, all right? So I can use this function called erase. So you can, of course, if you want to use this, you have to use the iterator again, make it point to the first beginning of the list, and then advance it to position so that it's like pointing to the third position, and then call the erase function, pass in your iterator. So the erase will know, oh, okay, just delete whichever node is pointing by the iterator, okay, which is this 16. So after you print out your list one again, you can see that you only have 1, 2, 3, and 5. Okay, so basically, these are some of the basic operations. As I told you, because if you look at the, just now I show you the list, right, where you can refer to functions in the list structure. You can go there and look at more operations that you can perform, like to sort the list, okay, to stop the list, and much more that you can do. Okay, you can try it yourself when you have time. Okay, now let's look at another linear data structures, which is stack our special. Okay, just now what we look at is a general list where our insert and remove can be anywhere, right? Any position in the list. But now we will look at the specialized list where the insert and remove can only be done from beginning or end. So the first one we see is stack. So what are stack? Okay, so stack are actually, let's see, if I want to insert item to stack, you see, this is how I will insert. I put item 1, item 2, item 3, item 4, okay, and so on. So every new item that I put inside the stack will be on top, right? Okay, and let's see. Okay, so stack is a special kind of list, right? Okay, as I mentioned. The insert and delete operation, if you go and find for stack, right, like on the internet, usually they will call it as push and pop. Push means you want to insert an item, and pop means you want to remove an item from the stack. Okay, and it has the property of default, last in first out. Remember just now I told you why? Because for example, like just now you see, how do I put all these item 1 to 4 inside? I put item 1 first, then 2, 3, and 4, right? So each of the new item will be put on top of the previous one, right? So now if I want to take an item out from this stack, which one I can take? Only item 4. Can I take item 2? Item 1? Cannot. You can only take item 4, which is the last item that you push inside your stack. Okay? You have to follow this rule. If you say that I'm using a stack, then you must follow the rule where when you push or insert a new item, it must only be inserted at the beginning of the list or the top. We call this as. When you want to pop an item, means you want to delete an item from the stack, you can only delete this item at the top. Okay, means now when I want to pop out an item, item 4 will be pop out. So for stack, you only have to keep track of the top of your list or the beginning of your list, because your push and pop or insert and delete operation can only be done at the position. It cannot be somewhere in the middle or at the back. No, only the beginning. Okay. If you follow this rule, then only this is a stack and it has the property last in first out. Okay. So stack is, of course, if you look at it, the insert and delete, it will be less general than list, and it will be much more easier to implement because the position that you can insert and delete is fixed one, only one position, right? Compared to the general list where it can be anywhere. Okay, so why do we want to learn stack, right? Because there are a lot of problems that has this last in first out characteristic. For example, let's say moving a set of boxes like this one here. How do you move? you will of course take the top one, then the second. After you take the top one, then second will be the top, then you take the second one, then take the third one, fourth, fifth, sixth, and so on. Right. Okay. Or reverse a list of objects. Now, stack is very useful whenever you have the problem where you need to reverse something. Okay, then you can use stack to help you. Okay, like for example, if this is how, let's say the boxes are placed, right? So when you pop everything out, you just have to push initially. How do you reverse? Initially, you push everything to the stack, and then you just pop out everything after that. Then you see the order of the object that you push in will be in reverse order after you pop out one by one. Okay, so to reverse something, stack is very useful. And also a programming function call, how it actually, how actually it is implemented, it is using stack. Okay, like first function you call is main, so it will push the main function to the stack. Second function, say function A, then function A call function B. So you push up. So after function B completed, then it will be pop out from the what you call it, the stack, and then the next function you go back to function A, and so on. Okay. Okay, and let's look at any specific problem. Last in first out property to solve means we need to use stack. Okay, one example will be how to check the proper pairing of the bracket. For example, you have this expression, right? And usually when we have this expression, we want to check this opening and this opening. You have opening, you must have closing, and it must be nested properly, right? Okay, if not, your expression will not be complete, right? Or it's not valid. Okay, so how do I write a program to check for proper pairing of this bracket? We can use a stack to help us. Okay, we will look at this example at the end later also, as the example for our stack. Okay, and also another famous problem that we can use stack is the Tower of Hanoi, where you use recursion usually to solve it, right? So recursion actually also like a stack function call. Okay, Tower of Hanoi, like games like Dungeon and Dragon. Okay, so Dungeon and Dragon, like for example, this is on backtracking. For example, when you are in the surface, you are in room D, then you go, let's say here, D, I go to room B, B, I go to C. Now, when I want to, after I go to C, if I want to go back to the surface here, what can I do? How do I know the way, how to go back? Then you do backtracking. From C, you go back to B, B, you go back to D. So to do backtracking, you can, it's a leaf-fall problem, so you can use a stack to help you to do this. Okay. Okay, now let's look at how do we implement stack. This is using list. Actually, if you want to implement stack, there are two methods. You can either use an array or a linked list. Okay, so use array will be something like this, right? You always have to keep the top element, and then but here we are going to use, because when we use the STL stack, it is actually using the linked list implementation. Okay, so for linked list, it will be something like this conceptually. If you use what you call that the linked list to implement our stack. So every time when we push a new item, you put it, you can say that as the first node in the list. Okay. When you want to pop item, also you will pop the first one. So you just have to remember for stack, right? We are going to both your insert and delete operation. The push pop can only be done at the first node or the beginning of your list. Then if you follow this rule, then you are using a stack. Okay. Okay. So let's look at the STL also provide the stack. Okay, but the stack here is not a container like this. It's just an adapter, which means that this stack and also the queue actually, they are built on top of the list. Okay. But how to use it is similar to the list just now. You can also refer to this link for the member functions that you can call when you use stack in, using this STL, the standard template library in your C++. Okay. So here I will show you some basic operation that you can perform using stack by using the STL stack. So first, of course, you need to include stack if you want to use stack, right? And then how do I declare a stack? You put stack here, bracket. What are the type that you want to store inside your stack? If integer, you put integer. Then this is the name of your stack. So when you just declare, your stack will be empty. Okay. Okay. And for right, is no iterator provided, because for stack, you don't need, actually we are not supposed to traverse the stack, you see. Okay, because for stack, what is important is your push and pop. Okay, your insert and remove, you see. Okay, so that's why for stack, no iterator provided if you use STL. But of course, if you implement it yourself, you can always traverse it, whether you're implementing using a linked list or using an array. Okay, but if you use the STL, there's no iterator like the list does not. Okay, let's see how do I add items to my stack. Okay, based on the code here, I will use a for loop from 1 to 5, and then first I will check if my stack is empty. Because I try to print out, okay, initially before I push the first item to my stack, if my stack is empty or not. So I can use this function called empty to try it out. Okay, so if it's empty, I will check stack is empty. I will print this stack is empty with what is the size of my stack, right? As you can see here, this is the output after I run this for loop. It will print stack is empty initially with size 0, because we haven't pushed the first item inside yet, right? Okay, when my I equals to 1, then I will use this function called push to insert item to the stack. Okay, so you just put s1.push and then followed by the value you want to push inside. Here we just use I. Okay, and then after that I will see out. Okay, here you see, remember I told you that for stack, what is important is the beginning of the stack, right, or the top. So that's why in the stack library they have this function called top, which will return to you the top item in your stack. So every time after I push a new item, I try to print out what is the top item now, so that we can see here. Okay, after we insert this, what is the top item and what is the size. So these are the output after I have run this for loop. Stack is empty with size 0. Then the first one, S1 top item is 1 after I inserting item 1, when my I equals 1, and S1 dot size is 1, right? Then when my I equals 2, now the top becomes 2 after I insert 2. Then the size of the stack is 2. After I insert 3, then my top is 3 after I insert 3, and then my size is 3. So you can see, okay? So this is, I mean, conceptually, this is my S1, where 1 is at the bottom here, then 2, 3, 4, and 5. And 5 is your top item after this for loop, right? You can see how the top item change every time you insert a new push a new value inside. It will be the new value that you push inside, right? Because we always push the new item at the top. Okay. Okay, to remove item from the, we use the pop operation, right? So if I want to pop out everything from my stack, this is how I will just use a while loop, where I always check, how do I know that I pop everything? Okay, the condition is as long as my S1 not empty, I know there's something still inside my S1. So I'm going to pop. So every time I pop, before I pop, because after you pop, this item will be removed. So we cannot see what is pop. Okay, so before I pop, I will print out the top item first, then only I copy. Okay, because if you pop first, then your S top will be the next item already. Okay, the first one is already pop. Okay, so we pop, we print the top first, then only pop. Then when my S1 becomes empty, I will print it's empty. Else I will print the size of my stack so that I know how many items I still have. So the first item I pop is 5, and the size now become 4. Initially it's 5, right? So the size become 4. Then the next item I pop is 4, and the size now is 3. Then I pop 3, then the size is 2, and so on, until finally, when I pop 1, my size will become empty now. Okay, because everything is pop up. So your while loop will be terminated. Okay, so so basically this is how I actually use stack. just a basic operation to manipulate stack only. Later we will look at we use stack to check the pairing of the bracket in the expressions. Okay, I think the first session is almost time's up. So I think we will stop here for the first session. So I will continue back I think around in 11:30, right, for our second session here, where I will continue with Q and also the example of using the linked list, stack, and queue. Okay, I think now we have to go back to the main channel, right? Okay. Yes, so we just leave room, another 5 minutes, okay. Okay, so you guys can go back to the main room for the another session. Okay, so we continue back for the second session here around 11:30. Okay, so I see you guys later. Stack size, there's no limit because if you use linked list to implement, then as long as you still have memory. But if you use array, then yeah, there might be the size of your array. Okay, guys, so I see you again later.